3.2, logarithmic functions. All right, this top line is probably the thing you need to keep in mind with what is a logarithm. The inverse function of an exponential function with base b is called a logarithmic function with base b, okay? Inverse function. So if you think about it before, you had before an equation y equals b to the x. That's what we saw in exponential. We have a base, it's to a power, we have this function. So if we do an inverse, we are flipping the x and the y, right? We flip the x and the y, and I say solve for y. Well, remember, in math in general, every operation there is, a mathematical function, there is an opposite function that undoes what you've done. We have adding, you undo adding by subtraction. You have multiplication, you undo it by division. You take something, you square it, then you take the square root to undo it. Everything has an opposite operation. How do you get y out of the power, right? That's where this comes in. This is where logarithmics come in, okay? This is why we don't see them on other type of things, because it's only when we're talking about a variable in this. And what we do is we use what is called a logarithm. The logarithm undoes the exponential, okay? They're opposites, they're inverses, okay? So the definition of this logarithmic is to basically take this exponential equation and pull the y out of the exponent spot, and we pull it out, and then we get log of base b to the x, or of x is probably the best way to say that there. Okay, so what that does is it pulls it out of there. Remember, when we're solving, we say all the time, can we leave a variable in the denominator if we're trying to solve for it? No, we can't solve for something in the denominator. Well, we can't solve for something in the exponent either. And this is the process that pulls that variable out of the exponent and puts it down to a level where we can actually solve for it. Okay, so that's where logarithm comes from. So one of the key things I need you to be able to do, and this is so key, if you don't get this pattern, you will struggle with logarithms, is you have to be able to easily convert from a logarithmic form to an exponential form, and from an exponential form to a logarithmic form, okay? You need to be able to move between them. So we need to make sure we understand the pieces. B is a base, either the tiny little, what we would call that subscript base by the log, or it's the full base that we would use in the exponential form. They are the same, okay? The base is the same. My exponent is either shown as outside when we pull it out in the logarithmic, or it is shown as the exponent when it's in the exponent form, okay? If you peek at that logarithmic form, there's no exponents anywhere. So it is taking it out of an exponent and pulling it out front. That's what it does, okay? So that b and that y are the same thing. And x is what your answer would be in exponential form, or the of part in the log, okay? The best way to do this is to follow example after example and just work on, can I pull them out of logs and into exponential? Can I change them from exponential and change them back into logs, okay? And yes, you're gonna hear me shortcut. I don't say logarithmic every time. I often just refer to it as a log, okay? So let's just work through some of these, and we're not even going to solve anything to start with. We're just going to change the form, okay? So on 1 through 3 here, they're already in logs. We want to change it back to exponential, okay? That's the flip. That's all we're doing here. So I always start with my base. The base is the tiny subscript. Now I make it my big number, so it's 2. My power, or my exponent, is always across the equal sign, okay? So that's my exponent. So I get 2 to the 6th power equals, and whatever remains here over on my log side is what it equals. 2 to the 6th power equals 64. Okay, if you plug that in your calculator, you would find 2 to the 6th power equals 64. But we pulled it out of that logarithmic form and put it into exponential. Okay, so let's try it again on number 2. Go to your base, that's that tiny b, now it becomes my big one, right? My power is always across the equal sign, or my exponent, b to the 5th power equals 32. Wow. Can't even write a 3. All right, now, some of you might be looking at that and saying, oh, I know what b equals, right? b equals 2 right now, because 2 to the 5th power is 32. Do you see how, because we pull it out of the log form, we could actually do something with it in the exponential form? And the key is, sometimes you want them in the exponential, sometimes you want them in log, so the more you can move between the two forms, the easier it is to solve these type of equations. Okay, So let's try our last one. Go to the little base, and that becomes your big base. 4, always what's behind the equal sign is your exponent. So 4 to the y equals 26. Now I'm going to be honest, I don't know how to solve that one. I would have been better off leaving it in the log form to solve it, okay? And eventually through this chapter, we will learn how to solve log base 4 of 26 using our calculator. But for now, I want you comfortable with moving in and out beyond the two forms, okay? Because sometimes one form is better than the other. We have to be fluent in moving between the two forms, okay? Let's go on to the second row where we're actually going to do it the opposite. They're in power or exponential forms, and we're going to change it back into the log form, okay? So the key thing is here is we just start off. I have a log. My tiny subscript is the base, which is my 5, of whatever the number here. This is kind of my of number, so 625 equals my power. The power is always on the outside, so 4. So I take it out of the exponential, and I move it back into the log, okay? This didn't do much for me algebraically, but I can do it. Okay, so let's try it again for number 5. Log, your big base is now your subscript base. The of x equals, the power is always on the outside, okay? And finally, the last one, log, take your big base and make it your tiny subscript of my 200 equals my exponent, which is y. And again, on this last one, that's getting my y all by itself. And again, if I can learn now the math that goes with log base 8 of 200, I can actually get a value for y. When it was up there in that power, it wasn't doing much for me, right? I couldn't solve for that exponent. You must be fluent in these 6 problems. Moving in and out of logarithmic and exponent functions, you must be fluent in it. You need to practice it. Okay, so let's go down here to 7, and we will see some of these on our test. And it says without a calculator, and I'm going to be honest, I want you to do without a calculator, okay? I have log base 2 of 64. I'm evaluating it, okay? The reason I'm not solving is there's not an equal sign. I'm evaluating. I'm trying to say, can I come up with a value for this, okay? So if you're thinking in your mind, by the way, I could kind of make it equal x because I don't know what it equals, right? So if I change that into a power, I'm thinking 2 to what power equals 64, okay? So if you're thinking about it in your mind, you might just think 2 to what power is 64? Okay, that's what this is saying. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. That was 6 2's, right? So the 6th power is what we get. So log base 2 of 64, if I evaluate it, it's 6, okay? So this next one is saying 81 to what power is 9, okay? So think about that, 81 to what power is 9? So let's see, what could I do to 81 to make it equal 9? I think I can take the square root of it, right? So that's the same thing because I wanted the power of saying the 1/2 power, okay? So 81 to what power? That's what I'm looking for is the power, so 1/2 would be my answer here. All right, last one here. I have log base 3 of 1 over the square root of 3. So I'm thinking 3 to what power will give me 1 over the square root of 3? Okay, well, the square root of 3 power, it would be 3 to the 1/2, right? But I'm in the denominator. How do I get that to a denominator? Remember, that's a position, right? That's that negative power, and a negative power does the flip, right? So it looks like if I did 3 to the negative 1/2, I get the same thing. So negative 1/2 is what I'm looking for here. Okay, so keep in mind all those rules we have for exponents because logs are using the same rules as our exponents. Okay, all right, page 2. We're going to graph these things. Okay, we need to go through some basic logarithmic properties. Okay. Log base b of b equals 1. because you're saying b to the first power equals b. Makes sense, okay? Log base b of 1 equals 0 because b to the 0 power equals 1. So those two are kind of, they make sense, right? You don't even have to think about the property. You could do the math every day when you see those, and you would get that answer. Okay, inverse properties of logs. This is important to know. If you have something log base b of b to the x, you basically, if your log to the base and the base power are the same, you can cancel and you just get the x, whatever is left, okay? Or if you have a base and the exponent starts out log base b, the b and the log base cancel and you're left with the x. So just kind of know that those go from there, okay? So on 10, when it says log base 8 of 1, it's saying 8 to what power equals 1? Well, 8 to the 0 power would equal 1. On 11, it's saying 7 to the power of log base 7 of 15. Well, my 7 and my log base 7, because they're the same base, they cancel each other. An exponent and a log of the same base cancel each other. They're opposite operations, and I'm just left with the 15 for my answer. Okay, now we're to graphing, right? So graphing these. Okay, some reminders, and I'm going back to what I highlighted to start this section. Logarithmic function is the inverse of an exponential function. Inverses switch the x's and the y's. That's what happens when you do an inverse. Okay? So if you think about the different properties, this should make sense. Remember, the domain of my exponential was negative infinity to infinity. I could plug anything in I wanted. That domain now becomes this function's range. And it's the old range of 0 to infinity now becomes my logarithmic's domain. So my domain now has a limit, okay? I'm going from 0 to infinity. I can't plug a negative into a log, okay? And that's going to be something we're going to keep in mind later when we're solving them as well. We can only use values from 0 to infinity. But the range, we're going to see every number used now. Okay, so we flip-flopped our domain and range from what we saw in the exponential function because that's what inverses do. So remember too, we used to always go through the point on the exponential function 0, 1. It's a flip-flop. We now go through the point 1, 0 with our parent functions, okay? So we go through the point 1, 0, which means now we don't have an y-intercept, but we have an x-intercept of 1. And now there's no y-intercept. So all of those features from our exponential function just do a flip-flop from our x's to our y's, okay? So if you think about it, our exponential used to have a graph that went up and to the right, and it evened out. Now we're going to come from the bottom and go to the right, okay? So it's going to do this inverse thing, okay? And that's if my base is larger than 1, and just the opposite, it will see if the base is smaller than 1, okay? Once again, we have an asymptote, but again, we change. We had a horizontal asymptote. This time we have a vertical asymptote, okay? And it's going to be the the y-axis, x equals 0, instead of the x-axis, which was y equals 0. So that flip-flop over and over and over, an inverse flips the x and the y's, and that's what's happening here. All right, so let's graph. We're going to think about what we did to graph our exponential functions, and we're going to use it to graph our logarithmic functions. All right, so we're going to start with the function, even an exponent, f of x equals 4 to the x, okay? So I'm going to make my chart x and y, and remember my y is 4 to the x, right? That's what's really coming in over here. So I give my values -3, -2, -1, 0, 1, 2, 3. Okay, and I'm going to plug them in. So 4 to the -3rd power, that's 1 over 4 to the 3rd power, so it's 1 over 64. 4 to the -2nd is 1 over 4 to the 2nd, so that's 1 over 16. 4 to the -1st is 1 over 4. Anything to the 0 is 1. 4 to the 1st is 4. 4 to the 2nd is 16. 4 to the 3rd is 64. Once again, this is what I graphed in the last section, right? This makes sense. So 1/64 is about at 0. 1/16 is pretty close to 0 too. 1/4 gives me up just a bit, and then I'm at 0, 1. I'm at 1, 4. And by 2/16, I am well off the graph. And I'm just going to keep going up and up and up from that graph. Okay, so this is my f of x. This is what I was graphing in yesterday's exponentials. Okay, now I'm going to graph its inverse, g of x. Okay, so g of x, you know what, let me go back one thing, because just to kind of reiterate this and make sure it makes sense. My domain over here, I could plug in anything I wanted, right? Negative infinity to infinity. No matter what I plugged in, I was getting closer and closer to 0, but I never dropped below it, so 0 was my limit all the way up to infinity. Did not include the 0. Okay, so now let's go for my logarithmic function. Okay. I have a real basic way to do this, but I'm going to be honest. I want to kind of show you, if all I give you is a log base, how would I expect you to do this, okay? So I do my XY chart. I'm going to be honest. I look at that and I'm like, well, how do I plug something in for x and get that y? I don't know, okay? Think of this as y equals log base 4 of x, okay? If I'm going to graph this on my own, I'm just approached, here's my equation, graph it. I don't know what to plug into x. I don't know how to do this. I don't know how to comprehend in my head what does that log mean. Turn it into exponential, okay? Just flip it. I'm going to go, remember, that's our key. We need to always be able to move. So I'm going to move it into 4 to the y power equals x, okay? That's something my brain can handle a little bit. Now, here's the key thing. I still don't want to plug in values for x. I'm confused. No one says we have to plug the values in for x. Why don't we plug the values in for y? I just need values. I need to calculate them. It doesn't say I have to plug it in for x. We usually always do. We call x that independent variable that we get to decide, and then y is dependent on it. Let's flip-flop them. We need an independent and a dependent, but it doesn't matter which is which. Flip-flop them. So I'm going to actually plug in for my y's. -3, -2, -1, 0, 1, 2, and 3. Okay, now if I plug in -3 for y, I'd get 4 to the -3rd power. Well, that's 1 over 4 to the 3rd power, so it's 1 over 64. I plug in the -2, right? Well, 4 to the -2nd power is 1 over 4 to the 2nd power, which is 1 over 16. I plug in the -1, 1 over 4 to the first power is just 1 over 4. I plug in 0. 4 to the 0 power is 1. 4 to the first power is 4. 4 to the second power is 16. 4 to the third power is 64. I have values I can graph. It didn't matter that I plugged them in for y and not for x. Now, I really want you to understand that process, because that's really how you should handle it if you're given it on a quiz or test. Turn it into exponential, make your XY chart, and you choose the y's and then figure out the x's. Okay, now let's go back to the idea of these are inverses. If these are inverses, could I not have just taken my XY chart from over here and flip-flopped it and made my x's my y values and my y my x values? Yes, that's what I just did. But sometimes we don't want to have to graph the first one to flip it for the second one. You can go straight to the second one and just flip what you plug in for. And I'm plugging in for the y's and finding my x's. Okay? All right, let me graph them so we can see where these goes. Okay, my x is 1/64. I'm barely past my 0, and I'm down at -3. Do you see that? And then 1/16, again, I'm barely past it. I'm down at -2. At 1/4, I'm barely past it, and I'm down to -1. And believe me, I don't have those accurate because it's such a tiny graph. And at 1, I'm at 0. Okay, so that's a definite point there. At 4, I'm at 1. At 16, I'm at 2. Okay, that's way off here, right? Oops, I would have to lift that up to 2. Okay, so that's like that. So here I am going across and right along that y-axis, and I'm going from here. Okay, there is my g of x, which is my log. Okay, think about this. If I was plugging in for my y's and I was getting these fractions, am I ever going to get something negative? No. So on my domain, that's what I was plugging in for. I didn't plug into, right? So we had to kind of just switch our thinking around here. maybe I should list my range first. I could plug in anything because I chose to make that the values I plugged in for. And for my domain, I got anywhere from 0 to infinity, okay? It's the flip-flop of my exponential function. Another key thing I want to show you here, okay? If you remember, it's the reflection across y equals x, right? Wow, that was a nice straight line. Do you see the mirror image if I folded on that y equals x list, okay? It's the reflection across that line. That's what an inverse does. Okay, so some key idea, this is what your normal graph is going to look like for a logarithm, okay? It's going to start over there and it's going to come from that fourth quadrant up to the right in the first, okay? That's kind of my, quote, parent function for any logarithmic, okay? And that's what we're going to base everything on, or we're going to do my transformations off of that. So if you ignore everything on the blue here and just look at everything on the red over here, the key things to graphing your log is to turn your log into an exponential equation, plug in values for y, and solve for the x, and then plot the points you find. Okay? Okay, so let's move on to the next page and talk about our transformations. Transformations, I'm going to tell you, this talk never changes because the only thing that's changing is the parent function, but what it does to our parent function is always the same. What's tightly connected to the x is horizontal, and we'll do opposite what we think it will, and what's not tightly connected to the x is all our vertical movements, and we'll do just what we think it will, okay? So once again, if we are adding in those c's on the outside and they're outside not connected to the x, we're going to go up or down. If it's tightly connected to the x, notice the parenthesis to tell us, hey, it's tightly connected to the x, it's in here, inside, then it's a horizontal move. Okay, the reflections, remember, not connected to the x is that negative out front, and it's going to flip that graph from top to bottom. Okay, but if we get that negative inside with the x, it's going to go from left to right. Okay, so if you think about that graph right now in that basically fourth quadrant to first quadrant, okay, if I do a vertical, which is the top to bottom, it's going to kind of start up along the y-axis and fall down, okay? But currently, without the reflection, it's starting down in the fourth quadrant and it goes up to the first and it starts climbing in the first, okay? So if I do the reflection horizontally, left to right, where it's coming up the y-axis and it's going to the right, it's going to go over into the second and third quadrants, and it's going to come up the y-axis and go into the left, up to the left in the second quadrant. Okay, vertical stretching and shrinking. Once again, if the C is outside, it's going to vertical stretch and shrink, just like we think. If it's bigger than 1, it stretches. If it's smaller than 1, it shrinks. If it's inside with the X, it's a horizontal stretch and shrink, and it does opposite what we think. If it's bigger than 1, it's going to shrink it, and if it's between that 0 and 1, because obviously the negative's separate, if it's smaller than 1, it's going to stretch it, okay? And once again, just like with exponential, it's hard to see stretches and shrinks, period. It's just hard, okay? But it does exist, so we'll keep that in mind. Okay, so I come down here, and we're going to start with log of x. Okay, quick question here. And I do need to do a little fix a typo here, I guess. It should be f of x, right? Equals x. Did I do a second typo and not put a base? Okay, this is really important to know, okay? And this is what we call kind of the invisible base. It's kind of like saying I have x. Well, what's its coefficient? It's invisible, it's 1, okay? So if there's an invisible base, and I'm going to call it that so that you know that it really is there, it's not a typo, but it doesn't have to be printed. If it's invisible, the base is always 10. Okay, so if you think about that, we deal in base 10. We count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start the repeat 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then we repeat again 20. So we keep going in base 10. Every 10 we kind of repeat our numbers, starting from 0 to 9, right? And we put a different number on front of it. That's base 10. So base 10 is the general, okay? I was waving my hands. You couldn't see me, and I changed screens. Anyway, invisible base is always 10, okay? That's super important to know on a log that your invisible base is 10. So we're going to go ahead and graph the parent function of f of x, right? And I don't want to write it like that. Okay, I'm going to choose my x's, and I'm going to get my f of x, right, over here is log x. Okay, taking a step back, f of x is log, our invisible base is 10 to the x. This is my y, right? So that's saying the same thing as 10 to the y power equals x, okay? So if this is my y over here, just think about this. I would rather plug in for my y, right? -3, -2, -1, 0, 1, 2, 3, and then solve for my x, okay? Because that's how I graph my logs, right? I plug in for my y's and solve for my x, okay? So 10 to the -3rd power, that's like 1 over 10 to the 3rd power, right? Which would be 1 over 1,000. 10 to the -2nd power, plug in -2, is 1 over 10 to the 2nd, that's like 1 over 100. 10 to the -1st is 1 over 10. 10 to the 0 is 1. 10 to the 1st is 10. 10 to the 2nd is 100. 10 to the 3rd is 1,000. Okay, obviously I can't graph a lot of those points. They're not going to fit on my graph. But the key is we plug in for the y's and we solve for the x's, okay? All right, let's plug these in. 1 1,000th, that's going to look like it's a 0, right, at -3. Okay, so my x is 1 1,000th. I'm down at -3, so I'm like right on my line. 1 100th is still going to look like I'm on my line at -2. 1/10 is basically going to look like, okay, I don't have to put it quite on there. It's going to basically look like the same thing too, right? And then I finally get to 1 0. And then I'm at 10 1. So you can see, like, obviously this is not going to grow very fast. It's going to be a long time till it keeps growing, right? But it will grow, because by 2 I may have to be at 100 before I reach 2. It's a long one, but it'll get there. Okay, so here's my f of x. That's my parent function. On my domain right now, so the domain for this one, obviously I'm not going smaller than 0, and I'm going to infinity. But my range, I'm going to hit every y there is, right? So -infinity to infinity. Okay. The range is never going to really change here. Domain will. So let's do some transformations of this graph. So the first one I see is log of x minus 3. Now, no parenthesis, which means this is not tightly connected to the x, which means it's going to be a vertical shift, and everything vertical does just what we think. It's going to go down 3. Okay. So I'm going to just take the points I already have and move them down 3, right? So I take this point 1, 2, 3. I'm down here. I have this point of 1, 0. I move it down 3, 1, 2, 3. And then everything else is going to move down 3, and we know they're right there along that line again. So it means that I'm just moving this down 3. There's my g of x. Okay. Did my domains change? What can I plug in? Exactly the same thing, right? I still am at 0 for my first value, and I go to infinity. Okay, so it didn't change. My range, do I get different y's? Even though I see that I come down some, eventually I'm going to use every y again. So my range is still exactly like I see. Okay? All right. H of x is kind of written in a funny form. Let's rewrite it. I don't like that 3 hanging out front. That's not where I like my constants. I like them at the end. So don't be afraid to send it to the end. Now, the negative doesn't belong there. So the negative I'm leaving out front, log of x. And then that's a positive 3, so I just put a plus 3 here. So what it looks like is there's 2 things happening. I have this negative out front. Well, it's not closely connected to the x, so that's going to be vertical again. And that will give me a vertical reflection. And that's what all negatives give me, are reflections. Okay, vertical means it's going to go up or down, right? And then this plus 3 means that I'm going to go, it's not tightly connected to the x again because there's no parenthesis. So it's also going to be vertical. And it's going to shift it just like we think it is, up 3. Okay, now the question is, what do we do first? Do we reflect first or do we shift first? Well, think about your x. If I was going to plug in a value for x, it would hit that negative before it would hit the plus 3. So I'm going to reflect first and then move it up 3, okay? So I have this point here. When I reflect, it comes down across it. Then I'm going to move it up 3. 1, 2, 3, okay? So it's kind of right above where I'm at. Okay, this next point, I don't really reflect a 1, 0 because it's on the reflection line, but I can move it up 3. 1, 2, 3, okay? So this next one, when I reflect it, it's kind of right here. I go up 3, 1, 2, 3, I end up here. I'm going to end up with all of these here. So what I end up with is this line. It still never touches that y-axis, but it's going upside down now because of that reflection. That's my h of x, okay? And it's not technically touching that f of x, right? They're not sharing a point, but with my bad graphing, that's what you get. Vertical reflection, reflect first because it's closer to the x, and then add the 3 and shift it up 3 seconds. Excuse me. All right, last one. I have log of x plus 5, and I have the parentheses that is holding that 5 tightly in with the x, which means I finally have a horizontal move, and it's going to be a shift, and I'm going to do opposite what I think it is. So plus 5 we would think would go right, but it goes opposite, so we're going to go left 5. Okay? All right. So take our values and just shift them left 5. So this one was at 10, 1, 2, 3, 4, 5. Here's my new one. This one was at 1, 0. Move it left 5. 1, 2, 3, 4, 5. That was on the point, okay? And then all of these kind of move 5 as well. So they're just right there along that line, right? And I end up with this graph that goes like this. So here's my k of x. Okay, big changes on this one. And I guess on h of x, I forgot to say what's the domain and the range. They would stay the same, okay? But because I moved horizontally, okay, and this is with the inverse, right? Now I have a change in my domain because domain was the one that had the limit on it. Because I moved to the left, it looks like I can go as far as -5, and then I go to infinity. The range is not going to change. I will get every value eventually, -infinity to infinity, okay? So with exponential, it was the range that had the limit of 0 to infinity, and then if anything happened to the y vertically, it could change that. But when we changed to the inverse now, and the domain became the one with the limit on it, now if anything happens to the x horizontally, that can affect the domain. And it's only going to affect it on a reflection or a translation or the shift, okay? Those are the only two that get changed. So make sure we realize that and the difference between them. I believe when we get to the test, I do ask you just for domains. I don't make you graph them. I just say, what will the domain be, okay? So remember that on an exponential, it's the range that's affected, and on a logarithmic, it's the domain that's affected, okay? All right, so just like it did down here, the domain of the normal one is anything that's greater than 0, but now as things change, okay? So I have questions like 14 and 15 here. There's my log, and I just say, what's your domain? Well, remember the normal domain is 0 to infinity. The only thing that makes a difference is if there's a switch in here and it goes opposite what you think. So the domain here is now going to become -6 to infinity because it would have moved it left 6, okay? And on logarithmic, that changes the domain. Okay, 15, I'm going to be honest, I'm not going to throw this at you a lot, but I want you to kind of know. There's a difference here, and I do want to make sure I state this. Do you notice this square? Okay, maybe think back to rational functions where we had the L shapes, and when it was just 1 over x, it was an L in the top right corner, L in the top, it wasn't really an L, but its reflection in the bottom left. But when we made it 1 over x squared, we ended up with kind of the L shape on the top right and then its reflection on the top left. We had those two. The similar thing happens here, okay? So let me give you just kind of a visual here. What happens is I have my logarithmic, and because I have -3, it moves it to the right 3. So I kind of have this function. Let me switch now. I kind of have this function where it comes right along this line here, and it goes off to the, oops, did I not switch? Okay. It kind of comes up like this. This is what happens, right? It moves this left 3, or right 3, I'm sorry. and I get this logarithmic function, okay? But what the square does is it's going to do just its reflection going this way, okay? So keep that in mind here. Okay, I do need to say something else. That doesn't say log. It says ln. Again, not a typo. We're getting into it on the next page. Log is with our numbers, base 10, base 5, base 7, whatever it is, okay? We're going to tend to do, we can do decimals. I'm going to be honest, we can do decimals. Don't worry about that. But just like when we did exponential and we did like 5 to the x power, 3 to the x power, 7 to the x power, whatever, we did one example that was a decimal and kind of a constant, and we did that e. Remember the e? Well, the opposite or the inverse of e is natural log instead of just log, and so they abbreviated it ln, okay? For this idea of domain and range, it doesn't matter whether it's log or natural log. It's still going to have the same principle. Okay, so we would start off my domain here, and I would say, well, I'm going to have 3, because opposite of that is 3 to infinity. Okay, but because we also end up with this second curve on the left-hand side, what I do is I go from negative infinity to 3. Notice the only value I can't touch is that 3, so it's going to be the joint union of those two values. Okay, so all the way up to 3 and then from 3 on. This is only if it's squared do you have a double and a intersection of, a union of the two, okay? So if we have on 14 just the normal, you're simply looking at that value that's changing your domain, and that's all you're going for. But if you are in anything squared, you have the double, okay? Not necessarily going to throw that to you a lot, but I'm just kind of throwing it out there as an example. Okay, 4th page. I was ahead of myself on that page, and I put that example using the natural log. Okay, so here's some general properties. We've already gone over some of these, right? That if I have base of to the 0, it equals 1, right? Anything to the 0 power equals 1. B to the first power equals b. B to the x power equals b to the x. We can cross off our log and our that. Okay, this is true. The only thing when we call them common logarithmics, okay, the difference here is these are base 10, right? So when that number is missing, the properties are identical. 10 to what power equals 1? Well, 10 to the 0 power. 10 to the first power equals 10. So it's that invisible base of 10, and the powers, the rules are the same. Okay, so when we go into natural logarithms, the key is we're talking about e, okay? So when you had y equals e to the x, okay, if I would put that into, if I would write log base e of y equals x, okay? Well, instead of writing log of base e, they switch it to natural log, and they just make it ln, okay? That's what that means. So this right here is replaced with ln of y equals x, okay? So your general properties, if you notice, these 4 properties right here match these 4 properties up here. Nothing has changed there. So now it's just saying if I use the symbol ln, natural log, instead of log, then you assume the base is e, just like when there's nothing written on the log, we assume the base is 10, okay? So again, it's not typos. This is what it stands for. Because this e is used frequently, they made its own log symbol, which is natural log. If you look on your calculators, in fact, I told you earlier, ln stands for natural log. My calculator has e to the x power, and its inverse is natural log. They're the opposites. You'll notice on your log button on your calculator that its opposite is 10 to the x power, because it stands for that, which, by the way, your calculator only has in it log base 10. It doesn't have any other log bases in it. It would be way too much memory for that calculator. We can still solve other logs, but we have to keep in mind our calculator only has log of base e, which is the natural log and e to the x power, and log of base 10, which is just the general common log, and 10 to the x, okay? So just kind of keep that idea in mind, okay? All right, so, excuse me, don't be overwhelmed with natural log. It uses the same properties and everything, only its base, keep in mind, is that 2.7-ish number, right? That's the only difference. It's the e. All right. So when I see on 16 here that I have natural log of e to the 7th, that's the same thing as thinking that I have log of base e, e to the 7th. Well, a log of base e to the e power, that cancels, and my answer is just 7. Okay, so if you see anything with natural log and e, you cancel them, and it's just whatever value is left. Okay, so if you think on number 10 here, remember, this log up top here is that base 10, so it's like 10 of log base 10, right? The missing is an invisible 10 of 44. Well, we know the property says that if I have a base and the power is log to that same base, they cancel, and I'm just left with the 44. Okay? Again, on 18, I see that natural log, so if I see e, I could rewrite natural log as log base e, right, of 5x squared. Well, that means my e is my base, my log base e, they cancel, and I'm left with 5x squared, okay? So natural log is just the base of e. Log with nothing in the base is base 10. And all of our logs are simply inverses of our exponents, okay? It's a lot to kind of take in. That's why the practice is important, okay? So please practice page 410, 3 through 8, 118 by 3s, 47 through 52 all. That's that graphing thing again, comparing the graphs. Please, please, please practice a few graphs. That is probably one of the most difficult things when people go to that test review at the end. They're like, how do I graph logs? Remember, change it to an exponential equation, make your XY chart, and plug in for Y and solve for X, and then use those as your ordered pairs. If you have questions, let me know.